Hello, friends. Today we're going to be investigating triangles. This is an investigation, so it's in the textbook that I'm using. It's separate from the regular lessons. It's an investigation. So we're supposed to do an activity, kind of find a pattern, come up with the formula for ourselves, even though they give us the formulas. So let's get into it. Okay, so here's a printout that you can find a link to in the description below. We have a regular triangle, regular quadrilateral, right, also known as a square, regular pentagon, regular hexagon. Regular means equiangular, all the angles are the same measure, and all the sides are the same length. So what we're going to do is we're going to measure the angles of each of these objects, right? And so I've got this handy dandy protractor. Again, I put the corner right here in the middle and line up the line. And then I'm looking to see, where does this line up? So this is 60 degrees. 60 degrees. Okay, so that means that all of these are going to be 60 degrees because they're all the same angle. The total then, the total here is 180 degrees, right? You add up 3 times 60 and you get 180 degrees. Then for the square, I mean, you should kind of know that this is 90 degrees, but you can measure it just to be sure. Notice that the line doesn't go all the way up, so I can't kind of see that, but you can take any straight edge. You could even use, like, you know, the pen itself and measure and like just line it up. You can see lines up with 90 degrees, but I can also use this if you have another straight edge or a ruler, line that up and you can see that it comes up here 90 degrees. So each angle is 90 degrees. Again, you should know that, but just to be all above board here, we're each of these 90 degrees. So that means the total is 360. Notice that's 180 more than the one we had before. Okay, now for the pentagon, go to the corner, line this up, and now I'm going to go over to this side, right? Again, lining up with the side to get the full range there. That looks like it's about 110, right? Maybe a little bit less. Tough to be exactly sure, right? Make sure we're all lined up here. Maybe just line up with the side. It looks like it's coming out just about to 110 degrees. So I'm going to call this 110 degrees. 110. So it's actually 108. That's what I thought. Okay, so I thought it was a little bit shy of that, but I was rounding to 110. But we're actually going to use 108. Okay, should come out to that. So really this is 108 for each of these. And the total comes out to 540 degrees. Okay, let's see. All right, and then the hexagon, line this up, using my straight edge to get out to here, and that's lining right up with 120. You can see that line right there. So this is 120 degrees. They're all 120, and so the total is 720. Okay, so what's the formula? Notice that these increase, the totals increase by 180 every time, right? 180, 360. This is basically, you can think of it as 1 times 180. This is 2 times 180. This is 3 times 180. And this is 4 times 180. Well, where do we get these numbers 1, 2, 3, and 4? How can we relate this to the number of sides? Well, 1 is 3 minus 2. So this is 3 minus 2 times 180. This is 4 minus 2 times 180, right? Because 4 is the number of sides. Again, I'm just coming up, seeing if I can find a way to relate the number of sides to these numbers that I have here. 5 minus 2 is how I get 3 times 180. And then this, I forgot to put the last parenthesis there, 6 minus 2 times 180. So notice that in each of these cases, it's the number of sides, right? So 3, 4, 5, 6. It's the number of sides minus 2 times 180. So the formula for finding the total, the sum of the interior angles is n minus 2 times 180. Each angle then is n minus 2 times 180, that's the total, divided by n, where n is the number of sides on the object. Okay, good. So there they are. interior angles. Those are the formulae. Okay, exterior angles. In order to do this, I have to extend these angles. So it's like I'm going to extend the side. It's going to go out that way. Lost a little bit there, but that's okay. Now I'm going to measure this angle and find out. So this is coming out to 120 degrees. Right. But here's the other thing too. I know this is 60. Since I know that that's 60, then I know that this angle here should be 120 because, not 120, because these two together should add up to 180. Okay, 120. And so then if I were to do this here and here, this would also be 120, and this would also be 120. 3 times 120 is 360. So 360 is the total of the exterior angles. I only count one of them. You know, you say, like, oh, well, you can go like that too, and then, right? No, but we're just looking at one from each vertex. On a square, this should be really simple. Again, you can use the protractor to measure, or you just know this is 90, so this should also be 90. So you have 90 for all of these, right? 90, 90, 90. And so the total here again is 360 because 4 times 90 is 360. What about our pentagon? The pentagon, we found out after a little bit of trial and error that it was 108 right, on the inside. So if this is 108 on the inside, then that means this here is going to be 72, right? And 72 times 5 is 360. Again, notice the total now is the same in every case. If this is 120, then we know this is 60 out here. And so 6 times 60 is also 360. So there's no formula for the total of the exterior angles. Every polygon, no matter how many sides, the sum of the exterior angles is 360. Each exterior angle then is just 360 divided by the number of sides. Again, this is true for any polygon, regular, irregular. This is true for each angle in a regular polygon, right? As long as we're talking about a equiangular, equilateral polygon. All right, so that's the exterior angles. Now we're going to take a look at the central angles. All right, here's how we find the central angles. What we do is we take the from each vertex, and then we draw a cross. Now, it doesn't really work for the triangle because when I go from the vertex across, it just kind of ends up tracing the sides. But for something like a square, we can do this. So you go that way, and we go this way. These angles here in the middle, these are what we would call the central angles. The central angles are the lines from the vertices to the center of each vertex, or sorry, from the center to each vertex. So you could think like this. Right? And so how many are there? Well, this one's pretty easy too. You just realize there's a circle here. So that's a full 360 degrees. So the way you get, so the total for all of these, again, 360, right? That's the total. And then to find the measure of each central angle, it's just 360 divided by 3. And that should come out to 120. Let's measure it just to be sure. Let's do this one here. All right. And so I follow that line, and that's coming out to 120 degrees right there. Okay, so this is 120. Again, the way I got that is 360 divided by 3. That makes sense. And then here also, this all the way around is 360. You measure that, you can measure it. It's pretty easy to see though that it's it's 90 degrees. Right. Going out 90 degrees, these are right angles. So again, 360 divided by 4 is 90. Now, if we're in the center here, this one I've got to kind of guess where the center is. And then theoretically, each of these angles is going to be the same. There's a more exact way of doing this, but we're not going to take the time to do that right now. But it should be obvious again here that each of these angles should be 360 divided by 5. Right, so the measure of each angle is 360 divided by n, just like the exterior angles. Right. And so 360 divided by 5 is 72. So this angle measurement should come out to be about 72. And you can tell I didn't draw this very perfectly because it's not quite coming out to 72, but because I didn't quite hit the center, most likely is the explanation. For the hexagon, this one we can, all we have to do is draw the across, and we should get what the center is. Okay, might be off a little bit. 360 divided by 6, so each of these angles should be 60. And we can measure that to be sure. And there you go, 60 degrees. So again, this is 360 divided by 6. 60 degrees. Seeing these triangles here reminds me there's another way to get the interior angles. Get the right paper here. So if we take a look at this, there's another way to derive this formula for the interior angles. Take a look at the square. What we can do is from one vertex, I can draw all the diagonals that I can. There's only one. So notice here I end up with two triangles. There are two triangles there. Now the sum of each triangle is 180. So it's 2 times 180 degrees, right? Because if I add up all of these angles, that should give me the sum of the interior angles for the whole thing. Right, and so I know these angles are all going to add up to 180, and these angles are all going to add up to 180, so 2 times 180. So that gives me this. That's what I had before, right? It gives me that same formula. For the pentagon, if I draw the two diagonals that I can from one vertex, right? So one vertex, there are two that I can get. How many triangles are there? Well, there are 3 triangles. So that means it's 3 times 180. And again, that's that same formula that I have there. For the hexagon, same idea. 1, 2. There are 3 lines I can draw, and so that means I end up with 4 triangles, right? 1, 2, 3, 4. So I have 4 triangles, and then that's 4 times 180. And that gives me the same formula that I had before. That's what I expect to get. So here, for the interior angles, you get 2 different ways of kind of deriving this formula for the sum of the total interior angles of the polygon. And that's it. So those are your formulae for interior angles, exterior angles, and the central angles of a triangle and any polygon. So thanks for watching. Don't forget to like and subscribe and share.